So the midterms are graded. I have the midterms with me right now. So I'll be handing it over maybe at the third part of the class when everyone are like more tired. Maybe not right now. Okay. And in today's class, we are going to discuss about an important concurrency primitive. It's called Semaphores. And along with that, if time permits, we may even discuss Deadlocks. And if we finish Deadlocks, then we are almost like done with concurrency. I was initially thinking about discussing another primitive called monitors, but I don't think we'll be discussing that in today's class, because it's okay even if we cover that or not, because you can easily understand based on how semaphores work. You can easily understand how monitors work, like if you want to like understand it later for some reason. And so we are like just pushing those topics to the end of the class. End of the course. If we have time, we will be discussing those things in the last 1 or 2 lectures. So the topics for the today's lecture. So the topics that we're going to discuss in today's lecture are semaphore. Initially, we will be only focusing on like what a semaphore is and how can we make use of a semaphore in writing concurrent programs. And in the next part of the lecture, we will be trying to understand, or we will be trying to implement our own semaphore. In the last part of the class, we will be discussing about an important topic called deadlocks. Before we start semaphores, let's just quickly review what are the different things that we have learned in concurrency till now. In concurrency, if you remember, we started with locks, like why locks are important in writing concurrent programs, and we saw like the hardware locks, like the different primitives like test and set, compare and swap, load, link and store conditional, and also we also saw something like the ticket locks and stuff like that, and we also saw some software locks. For example, the Solaris lock that we saw in the last class, which had the park and unparked primitives, are basically software locks. And after locks, we moved into like condition variables. We saw like just locks are not enough for writing correct concurrent programs. We need condition variables too. And the important reason for using condition variables is like ordering. If you want to order like 2 events or a set of events, then we'll be using condition variables to order those. For example, we saw the join problem in the last class, where we saw like if the main thread wants to wait for the child thread to finish, then we can use condition variables in that case. The 2 primitives that we saw in the condition variable was wait and signal. If you remember, wait gets in as arguments the condition variable and the mutex lock. The signal just gets in the condition variable. And when a thread calls wait with the condition variable and the mutex lock, we are basically going to place that thread on a queue on the condition variable. Condition variable is just a queue, so we are going to place that thread on that particular queue. And the assumption is the wait assumes that the thread that is calling wait has already acquired the mutex lock m, and so when inside wait, in the implementation of wait, that mutex lock will be released, and immediately that thread will be put to sleep, right? And when someone signals that particular thread on the same condition variable C, then that particular thread, before it wakes up, in the implementation of wait, we are going to like acquire the mutex lock again and then wake up. Okay, that's how wait and signal works in condition variables. Now, yeah, this is what we saw, and we also saw how to use condition variables in the producer-consumer problem or the bounded buffer problem. We saw how to use these things, and the final solution actually used two different condition variables, okay, called empty and fill, and we also made sure that we used a while loop for the final correct solution instead of just an if statement, right? The semaphores. In this class, we are going to like look at a different concurrency, like a tool called semaphore. So we may take this particular handout where we have a pseudocode for semaphore. So first, let's just go through this particular thing. So if you don't have this handout, there are like 4 handouts that I kept here. Yeah, all that. Yeah, let me just come and pick it up. Sorry. So what we have here is just a pseudocode of like the different routines that we have in a semaphore. And at a very high level, we can use a semaphore for as both a lock and a condition variable. That is one like important use case of semaphore. We can use a semaphore as both a lock and a condition variable. We will be looking at how. But before that, initially when we start, okay, there is a method routine called seminit, okay, and which takes in the semaphore. Sem underscore t just stands for, it is the type. We have a variable of type sem underscore t, which is a semaphore, and it takes some initial value. So initially we can just assume that we really don't know how a semaphore is implemented. If this is a semaphore, it is having some field called value, okay? It has some field called value, and initially we may initialize that value with whatever we desire, okay? That is what seminit does. So the way that you may use seminit somewhere is you just call seminit with that particular, if this is a semaphore that we are using, with a particular semaphore there, and you may give some value. Let's assume any value like 0 or 1, or it depends on the use case that we are going to use. Okay, so if this is how you just call this particular thing. In sem wait, okay, the two important routines in a semaphore are wait and post, very similar to wait and signal in condition variable. But what wait does is it just decrements the value that we have inside the semaphore, this particular value inside the semaphore by 1, and immediately checks if that value is less than 0, and if so, it puts the thread to sleep. Okay, and in the post, it just increments the value by 1, and immediately it wakes up any thread that is already sleeping, if there is any thread that is sleeping on this particular semaphore. This is how it is done. And one important thing to note here is like both the routines like wait and post should be atomic. Only if they are atomic, then this would work, then semaphores would work. Okay. So now we just saw these three things: sem init, sem wait, and sem post. The first task is to just see like if this would really help in some way. Okay, we can take this handout where we say like using a semaphore as a mutex log. So now the task here is just going to be we have some code that we are already familiar with, like creating two threads, and the threads try to increment the same counter, the shared counter here. Okay. Now using this particular definition of a semaphore, okay, using this particular definition of some semaphore that we just saw here, now the task is, you should first try to see if we want to use this semaphore as a mutex log. Okay, if you want to use the semaphore as a mutex log, what should be the value that we should initialize this semaphore with? Okay, that's the first question. What should be the value that we should initialize this semaphore with? This is the first thing that you are going to look at. And how will you use the semaphore? Like, what are the two lines that you will add here and here? This is the second task, and this is the third task, to actually use a semaphore as a log. So I think tasks 2 and 3 are straightforward, but the first one thing that you may need to think about is what is the initial value that we should give this semaphore, that we should initialize this semaphore with, so that this semaphore can be used for mutual exclusion. Okay, just think about it for a few minutes. And also remember, in this case, there can be like more than 2 threads. You should also think about cases where, like, let's say there are 3 threads that are trying to acquire the same log. Then will the value that you are initializing the semaphore with, will it still work? Okay, let's see this. So first let's just see, like just put some value like 0 and see if 0 can be an initial value for this particular semaphore. Okay, so if we have 0 here, then when the first thread, okay, when the first thread is trying to use like use the semaphore as a log and enter the critical section, as we can see here, if from these two routines, wait and post, you can easily see that wait is the one that is going to be used as a log, and post is the one that is going to be used as an unlog. And so if we use like sem wait on and call this particular semaphore, that initial value of 0 would be decremented to -1, and at line 10 we will be checking if that value is less than 0. Yes, it is, and immediately the first thread which is trying to acquire the log will go to sleep. Is that right? And so 0 cannot be an initial value for this particular thing if you are going to use it as a mutex log. Let's just try 1, okay? If we are having 1, if we are having initial value of 1, then let's just take this case And okay, the initial value, if we have it 1 here, and the 2 lines that are to be added here are sem wait on the particular semaphore, and once we are done, we can just call sem post on the same semaphore. Now let's see if there are 2 threads, T1 and T2, how will this work, okay? And let's just have the value of the semaphore here, okay? S dot value, you can just have the value down here. Initially, we are having it as the value 1, okay? When this is 1, and if thread 1 is trying to enter the critical section, it will call wait on that particular semaphore, and when it calls wait, the value will become 0, and 0 is not a negative number, it's not less than 0, and so now after calling wait, this particular thread may enter the critical section. Okay, the first thread, you can assume that the whole thing is the critical section, it has entered the critical section and it is doing some job there. But while it is in the critical section, let's assume thread 2 calls wait somewhere here. We can assume that the time runs in this direction from top to down. Okay. And if thread 2 calls wait at the same time, then the value of the semaphore is going to become -1, and clearly -1 is less than 0, and so this particular thread can't enter the critical section, but in turn it just goes to sleep. Based on the definition of the semaphore, we can see that if that value is less than 0, then immediately the thread will go to sleep. Okay, so now this thread has gone to sleep. And now let's assume, so the value, this value is going to remain as -1 for a long time. And then when we call post here on the same semaphore on thread 1, now all we are going to do is just increment that value by 1. In this case, the value is going to just become 0, and then we are going to wake up one of the threads that are waiting on that particular semaphore. So let's assume here, since there is only one thread, we just wake this up, okay? So once we wake it up, what is going to be the value of this semaphore, S dot value? Is it going to be 1? Or is it going to remain 0? So it's just going to remain 0 because this thread that went to sleep based on our definition, okay? Based on our definition, this thread that went to sleep was here, okay? Was at this point, okay? And when it wakes up from this particular sleep, it just proceeds. So it just proceeds down. So when we proceed, this sum weight is done. Once sum weight is done, it basically means we enter the critical section and the value is not altered anywhere here. And so the value just remains 0. And this keeps on going. So now this is in its critical section. This thread is in its critical section. And finally, when this thread is done, it will call post on the same semaphore. And at this time, this value is going to be updated to 1, which is the initial value that we had the semaphore, okay, that we had for this particular semaphore, and it's done. So now 2 threads work in this particular way. Can you think what will happen if there are 3 threads that are trying to enter the critical section? Will the same initial value of 1 work for this particular semaphore, or wouldn't? So if you think about it, it's actually going to work, because we can just try adding a 3rd thread here, okay? If there is another thread, if it had called wait here, okay? If it had called wait here at this time, just this value would have been decremented one more time. So I will just write the S dot value here with the 3 threads, okay? The 3 threads case. So S dot value initially was 1, and then the first thread calls wait, it becomes 0, second thread calls wait, it becomes -1, the third thread calls wait, it becomes -2. Okay? And then it just, whenever the first thread calls post, okay, whenever the first thread calls post, it just becomes -1, second thread calls post, it becomes 0, and let's assume this was the time this thread woke up, okay? this third thread wake up and it runs in its critical section. Finally, when it calls post, it's going to set this value to 1, and this is going to work. Okay, and this definition of semaphore, like whatever we saw, the pseudo code here was first implemented by a person called Dijkstra. I'm not sure if I'm pronouncing his name correctly, but yeah, this is the person. You may have already known him like in the shortest path algorithms, data structures that you have studied, in the graph algorithms. And so he has done a lot of work on concurrency. So most of the things that we study in concurrency were actually like, he was one of the important persons behind all those things. He's credited for inventing semaphores. And the coolest thing here is like now we just used a semaphore as a mutex log, like this, right? And so these semaphores, practice, they are called binary semaphores. They are called binary semaphores. It just usually these are just used for mutual exclusion, okay, for implementing mutex logs. The other use of semaphore, as I already told you. Yeah.
Would there ever be a case when the S value is more than 1?
In this particular definition?
Yeah.
I don't think so. So, will there be a case when in this particular definition of semaphore that we have, will the S value be more than 1? No. So, S value, the initial value will be, since we set it to 1, we can make it more than 1 in the sense, in this particular case.
No, I was asking like if we set it to 1 initially.
No, yeah. So if we set it to 1, in this particular case, it's going to be 1, unless you, you don't use those primitives properly. In the sense, if you call a post without calling a wait, then it can be more than 1. But if it is used in this case, in a way that we just used as a log, as a mutex log, then its maximum value it's going to go is 1. And whenever it has some negative value, usually in this particular definition of semaphores, it just corresponds to the number of threads that are waiting for that particular log. Any other questions? Okay, so the next thing that we're going to see is how can we use this semaphore as a condition variable. So if you just turn this sheet, this was the same problem that we saw in the last class. Like we are trying to print the parent begin as the first line, then we should print child, and then we should print the parent end. So we are trying to order these events in a certain way that these two threads are among these two threads, we are trying to order these events. So in last class, usually the easiest thing that we can do is just to use a p-thread join here, right? Because p-thread join basically makes the parent thread wait for the child thread. But in last class, we saw how can we use condition variables to make that implement something like a join. Do you remember? So the two things that are needed are in condition variable, you should use a condition variable with the mutex log, and along with that we should also have a state variable. If you remember, we had something like done, and we would be using both the combination of the condition variable and the state variable to make this ordering. So now the task is, can we use the semaphore that we just saw to actually order these events? Or in other words, can we use a semaphore as a condition variable in this case? Just think about it, maybe 2 minutes, and let's just discuss. Again, the three things that you have to just think about are here. So how would you initialize this semaphore? What would you write here? And what would you write here? Just these three things. That's what you have to think about. Just the three primitives are semInit, semWait, and semPost. Okay, can someone tell me if you have figured it out, like what should be the initial value for this particular semaphore? So we're just going to write semInit here, okay? And we have the semaphore here, sem_ts. So what is the initial value that we're going to have for this particular semaphore? Zero, yeah. So here, initial value is going to be 0. Let's see why, okay. So at this point, we want this main thread to wait if the child thread hasn't executed it. And so this is the place where we are going to use the semaphore, the routine semWait. Okay, and when the child is done, it's just going to signal the parent thread that I am done and you can proceed. And so in this case, you can just write semPost of this particular semaphore here. Okay. Now let's see how this works. First, let's think about the condition where let's again have the value of the semaphore here. If yes, it's the value of the semaphore, and if this is the main thread and if this is the child thread, okay. Initially, we initialize it to 0, the value of the semaphore, we initialize it to 0, and let's assume when the main thread, when we create the child thread, and there are two conditions here, right? Either the child thread can run or the main thread can run first. First, let's just assume the main thread proceeds. So we come to line 25, even before the child starts executing, and so when we come to line 25, we call a semWait, and semWait is going to decrement this value by 1. And the main thread is calling semWait here. Going to decrement this thing by 1, and it's going to go to sleep. Let's put to sleep, okay? And at this time, let's assume child is executed. When child is executed, at some point in time, again the time runs this way from top to down, okay? Some point in time, if the child calls this post, so now the child is going to make this value to be 0, okay? Make this value to be 0 and wake up this particular main thread that's waiting on that particular semaphore. And so now when the main thread wakes up, the main thread isn't even going to check that value again, because we know that there is just if condition there in the definition. Again, go back to the definition just for clarity. Main thread would have been put to sleep at this point, so once it wakes up, it immediately proceeds, okay? And so once this post is done and this main thread is woken up, wake up this main thread. So now the main thread proceeds. That's it. So now we have ordered this, okay? So now this is a case where, this is one case. Now the other case is, again, let's assume yes, the main thread and the child thread. And now let's assume that S starts at 0 and the first thing that runs is the child thread, okay? When the child thread runs initially, so now what is going to happen? Child is going to call a post, okay? And so when the child calls post, the value is going to become 1. Value of the semaphore is going to become 1. And let's assume child, once it calls post, it will try to wake up some thread that is waiting on this particular semaphore, but there is no thread that is currently waiting because the main thread hasn't called wait yet, okay? And so it doesn't wake up anyone basically. And let's assume the child is done here. And when the main thread is executed, if the main thread calls wait at this time on that particular semaphore, the value is just going to become 0. And 0 is not less than 0, it's not a negative number, and so this thread, the main thread, is not put to sleep. Okay, the main thread just proceeds. Main thread is not put to sleep. Because as we see here, the main thread would have decremented the semaphore's value from 1 to 0, and it is not less than 0, so this condition would not be executed, so it would just proceed. Does it make sense? Any questions here? And this is how we use a semaphore as a condition variable. But when we use a semaphore as a condition variable, we are really not using a separate state variable here as we did with condition variables for enforcing ordering between events. You can just use a semaphore directly. Any questions on this? Okay, this is the producer-consumer problem that we saw in last class in that handout. Here we have the do-fill method. We'll just go through this quickly. We have the do-fill method which fills the buffer. We have the do-get method here, which the consumers use to get an element from the particular buffer. So we have the producer, and in this code, the producer just loops times. The loops is the variable, how much times we are going to loop and fill this particular thing. We fill those buffer, and when there is an end case, okay, and after those many elements are being produced, the end case is just to fill the buffer with -1, so that each consumer, whenever it reads an element of -1, it just assumes that the production has been over, and so it can also terminate. So, but we really don't need to worry about this end case really in whatever we are going to discuss today. So the consumer just checks if that thing is -1, if the element that it gets from the buffer is -1, then it just stops. Okay. And yeah, we have the main code here. So now what we are going to do is, we are going to see how can we use semaphores for making this producer-consumer problem to be thread safe. Okay. So the first thing is, so here we are having like two semaphores. In the first try that we are doing, we are having two semaphores with empty and with the names empty and full. So important things to note here are lines 78 and 79, where we are initializing these two things. Okay. So max is the maximum size of the buffer, and we are initializing this semaphore with the value of max, and we are initializing another semaphore called full with the value of 0. Okay, and the way they are used, the producer just waits on the semaphore called empty, and it signals on the semaphore or posts on the semaphore called full. Okay. In a similar way, this is very similar to how we used condition variables, like two different condition variables. In a similar way, in the consumer just waits on the semaphore called full and it posts on the semaphore called empty. Okay. So now I'll just maybe even remove this edge case as of now, the end case. We don't need that. Okay, now whatever we need is like right before us, okay? Just we need these four routines: do, fill, do, get, producer, and the consumer. Now can you think, like, will this usage of semaphores work, or is there any issue here? Okay. Again, the semaphore, we'll just see what are the initial values. Empty is initialized to max and full is initialized to 0. Let me just write it down here. So are there any issues? Can you think of any scenarios where this may cause an issue? So the thing that is happening here is, okay, whenever a producer wants to produce something, it just calls a wait on this particular semaphore. So the value of empty will be decremented by 1, and it will check if that value is less than 0. If so, producer goes to sleep, because it means that the maximum size or the maximum number of elements are already there in the buffer and no element has been consumed yet. If not, it will just proceed here. It will just do a fill and then it will just call a post on the full semaphore. The full semaphore is the one that consumer is waiting on. So as we saw, the full is initialized to 0. So if the consumer starts first, okay, the consumer is going to call a wait on the full semaphore here. It starts at 0, so it decrements it by 1, it becomes -1, and immediately, if there is no element that has been produced by the producer yet, it goes to sleep, right? The consumer will go to sleep, and once the producer produces an element, it just comes here, and then calls a sem post on the full, and immediately this consumer wakes up, okay? Are there any issues here? So the hint is, think about a case where there are like 2 producers, okay, where there are 2 producers and just 1 consumer. Think about a case where there are 2 producers that are trying to fill the buffer, okay, and one, or like the number of consumers really does not matter. Multiple consumers that are trying to consume. What may happen in this case, or what is the problem that can occur here? Is the code visible at the end? It out. Again, the reason I could just go through each of the things like normal lecture where I just directly tell the solutions. The only reason we're giving the time for you to think is like the questions that we'll be having on exam on semaphores, or like in general whenever you're working with concurrent code, situations will be like this. There will be a bug in code, a code like this, and we would just experience like, we know like something is wrong, but the way that we should be debugging is like thinking of different conditions that may, or different cases that may happen, and so just to simulate that environment is the only reason that we are giving you, like reason I'm giving you time to think about the problems here. it would be easy from my perspective just to directly tell and just keep on going. Okay. Just try best effort. So the problem here is, okay, anyone want to try? Yeah. Yeah, like, exactly, yep. And how, or like, why do you think that will happen?
Well, because we don't actually wait for one, so because the MPQ is initialized to max, so we're not actually going to put them to sleep until we figure it all the way down.
Exactly, so that's correct, great. So the thing is, we have initialized the semaphore empty to be max, right? So let's assume if the maximum size of this buffer is 10 or something like that, okay, some number. So what the first producer will do, it just comes here, it decrements that value of the semaphore by 1 and sees if it is less than 0, it will go to sleep, okay? That particular thread will be put to sleep, but if not, it will just proceed, right? When it just proceeds, we call do fill, okay? And we are inside do fill. At the same time, if there is one more, and let's assume we have like a context switch at line 23, okay? At the same time, when a second producer is trying to produce, the same semaphore empty would be decremented by 1. It may not be still less than 0. If the max is, let's say, 10 or 3 or some value, it may not be less than 0. And so immediately what is going to happen is the second consumer can also, second producer can also call do fill at the same time. And the problem easily arises because do fill is a method that needs mutual exclusion because we have the shared variable called fill PTR and it uses a shared buffer, right? And so now it is easily possible for the two producers to overwrite each other's work just by how scheduling may happen between the lines 23 and 24. Does it make sense? So the idea here, the problem here again is if this is the shared buffer that we have, 0, 1 and 2, producer 1 may be trying to fill in this particular element, produce its thing here. At that time, if there is a context switch, okay, at line, let's assume it just filled that particular thing, buffer of 0 equals value, and before it updates the particular fill pointer's value, if there is a context switch and if other producer comes in, the fill pointer would still be 0. At that time, producer 2 is also going to produce its element. Let's assume P1 writes an element of 1. P2 will just overwrite its produced value right here, right? And then P2 may increment it, and now the fill pointer may be pointing here. But when P1 comes back, it's just going to increment fill pointer by 1 and just proceed. But whatever element that P1 just produced is gone because of this untimely context switch between the two producers P1 and P2. And that's why this solution is not going to work. Okay? So what do you think we need here to make the solution work? Exactly, so we just need a lock to protect the critical section. If we are going to use semaphores, okay, we are just going to say something like, we are just going to add, let's say, like one more semaphore called mutex, okay. Let's add this new semaphore called mutex, and all we are going to do is, maybe you should initialize it with a value. So what should be the value here for mutex? The initial value for mutex is just going to be 1. As we saw here, if you are using a semaphore as a mutual exclusion lock, okay, as a mutex lock, the initial value is going to be 1 because only one thread should be inside that particular critical section. And now what we can do is, we can easily say something like, just copy this line. We can just add a sem wait on the mutex, also a sem post on the same mutex. And similarly, the same problem may occur in the consumer also. Okay, in the consumer also same problem may occur, and so you just protect this particular critical section of a do get. Okay. Now, the question is, we just added this, we have protected the critical section. So now when the first producer comes in, it takes the mutex lock and then it calls the sem wait on empty, and then we do a do fill. And so when the second producer comes in, second producer will be blocked at line 37. Because we are using the semaphore mutex as a mutex lock, so it will be blocked at line 27 and it will not be able to produce. So only one producer will be able to produce at a time. Okay, I mean, will be able to like fill in the buffer at a time. Yeah. So, are there any problems in this particular piece of code, like, or at this time? So at this time we are just like, okay, you mean like since we are using the same mutex lock for the consumer also, okay, then in that case we can actually try using different mutex lock if that is the problem, but we should think through that if that will create any new problems. So in this case, as it is, as we have these mutex lock, okay, does it work, or do you think there can be a problem here?
The thread could get the mutex lock and then fall asleep, and then nothing could wake it up again because it's locked everything else out of the sem posts. So
are you thinking of it like from the perspective of a producer or a consumer?
So if a producer gets the mutex lock and then it's full, the producer will fall asleep, but then the consumer can come in and get the mutex lock to empty it.
Exactly, yeah. So let's assume a case where there is just like a single element in the buffer, okay? When there is a single element in the buffer, when we acquire, if the producer acquires a mutex lock and then it, it calls a wait on empty, and if that is 1, I think, I'm not sure if this case would create a problem. Okay, let's assume the max is 1 at this point, okay? If the max is 1, then what will sem wait do? We are not going to sleep at this point, right? We are just going to produce, and so that will keep on going in the say like a do fill will happen, and then a sem post on full and a sem post on mutex. But if the second time, if it's trying to produce a second element, then it acquires a mutex lock again, the producer acquires a mutex lock again, then it comes to wait. At this time, we are going to sleep, this producer is going to sleep, and yeah, it creates a problem. At this time, the producer is going to sleep, so if any consumer wants to consume an element, it needs to acquire the mutex lock. But the producer just got the mutex lock and went to sleep. Does it make sense? So, we can think of the same problem in a different way also. So, the other way to think about is, what if the consumer just started running first, okay? If the consumer just starts running first, initially, consumer is going to get this mutex lock. We are going to call a sem wait of full, but at this time, there is no element in the buffer. And so this consumer is going to sleep, right? And for this consumer to wake up, there should be some producer that should be able to produce an element, okay, and call sem post on full. Is that right? Should be able to call sem post on full. But a producer will not even be able to produce anything, because when it tries to acquire the mutex lock at line 37, it will not be able to do so, because the consumer that just went to sleep at line 51, okay, consumer that just went to sleep at line 51 has the mutex lock. And remember, the semaphores are not like the condition variable where when you go to sleep, you release the lock and go to sleep. Okay, it just has the lock with itself. And so this creates a problem, and this particular problem is called a deadlock. Okay, so the consumer is waiting for the producer to wake it up, and the producer at the same time is just waiting for the consumer to release the mutex lock. If the consumer releases the mutex lock, then the producer will be able to wake the consumer, and so there is a dependency here. So the dependency that's happening here is, if this is the producer and if this is the consumer is waiting on the producer, wait to be woken up by the producer, and at the same time the producer is waiting for the consumer, is waiting to release the mutex lock. And this creates a cyclic dependency between the producer and the consumer, and this eventually leads to a condition called a deadlock. We'll be discussing more about deadlocks the last part of today's class. So how can we solve this particular problem? How can we make this work?
Use a different mutex for the consumers and the producers.
So one of the solutions is to just use different mutex locks for the producer and the consumer. Will that work? But they are using the solution is to use different locks for both the consumer and the. No. I think that will work. Using two different locks will work, but maybe you should think through it much more detail, just to make sure if that particular solution will work. But based on whatever we see here, because it is more like the producer is going to use a different lock and the consumer is going to use a different mutex lock, both will not interfere in each other's thing. Okay, if that is one, yeah. Exactly. So if you want to just use a single mutex lock as we have here, the solution to do so is just move this mutex lock, okay, inside. I mean, just before the do fill and the do get. Just think about this. So now we have the same mutex lock, just protecting the do fill and the do get, and this is not going to now, so let's think about the same scenario now. When the consumer runs first, it's going to call a sem wait, and it's going to go to sleep because there is no element that is there in the buffer. and at this time it is not acquiring the mutex log because it went to sleep at line 50. When it went to sleep at line 50, we still don't, this consumer has not yet acquired the mutex log, which is good. And so now the producer can run. The producer again calls semwait. Let's assume the buffer is like some 10 elements or something. So this is not going to sleep. And then it's going to acquire the mutex log, do a fill of the buffer, then do a post. Release the mutex log in this case, and then do a post on full. And this is like when we post on the full, this particular consumer that was waiting here at line 50, now this is going to wake up. It's going to wake up, acquire the mutex log, get an element from the buffer, release the mutex log, and then just proceed. Are there any issues with this particular solution?
Can we change that post to wait?
Oh, sorry.
The consumer.
This one? Oh, sorry, yeah. This is just a typo.
Yeah.
Post here. Yeah. Let's assume if this is the solution, do you think will this work?
At line 50, for instance.
Line?
Line number 50.
Okay.
If you wake up right after line number 50, you still need to check the condition again.
No. So it is just using an if thing here.
Right. Makes sense. Yeah, so that should work, right?
Yeah.
That should work. So there's no need to then check the condition.
So yeah, this is like a working solution for using semaphores with condition variables. Okay. Are there any questions about this? Okay, so then we can take a break right now, and time is 6:31. So the next thing that we are going to see is a lock called reader-writer lock. Okay. So initially, I just want you to go through this particular code snippet and just try to understand what is the benefit of this particular lock. So the important routines that we are interested in are the read, write lock, acquire, read lock. Okay. So okay, first the thing is inside this struct we have a semaphore called write lock, we have another semaphore called lock, and we have an integer variable called readers. Using these three things, people have implemented something called read write locks. Okay, and the scenario is, you can assume there is some shared buffer, okay, or shared buffer, and there are multiple readers that are trying to read from the shared buffer, and at the same time there are multiple writers that are trying to write to this buffer. Clearly, the idea here is two writers should not be allowed to write at the same time. So at any point in time, only one writer should be able to write to this shared buffer. But we should think about the case when the multiple readers that are trying to read. Is it okay to allow all the readers to read at the same time? Unless one important thing that we should take care here is when a reader is reading the shared buffer, any writer should not be able to update that particular buffer. Okay. So under this scenario, try understanding what is happening in these four routines. Okay, and then we'll just go through in detail to make sure if we understand how this particular lock works. So there are two types that there are two ways in which you can acquire the lock. One way is you can acquire the this particular lock as a write lock. So writers usually acquire the write lock, the readers acquire the read lock, and I think the write lock is straightforward, but try understanding mainly these two routines where the readers are trying to acquire the lock, the read lock, and how the readers are trying to release the read lock. Okay, let's try to understand this. So initially in the init routine, we are just initializing the readers, number of readers to be 0, and then we are initializing the two semaphores, lock and write lock, to the value of 1. So basically both these two semaphores, lock and write lock, are going to be used as mutex locks. And so first let's look at these write lock routines. In the write lock, we just call a sem wait on the write lock. So after that, any thread that is trying to call an acquire write lock will not be able to do so, because we have already we have used the semaphore as a mutex lock here. Okay. So at this time, when a particular thread is doing a write, let's see if another thread can just read. Okay, if a reader thread comes in and if it tries to acquire the read lock at that time, it goes and acquires a thing called lock. Okay, this is a different lock just for protecting this particular region of code, like 17 to 19, and then it increments the number of readers to 1, and it says if the readers count is 1, then the first reader, only for the first reader, this counter is going to be 1, this value is going to be 1, and then it does a sem wait on write lock. So at this time, when it does a sem wait on the write lock, the first reader will not be able to proceed, okay, will not be able to acquire this lock, or in other words, it will be just put to sleep, right? Because the scenario that we are assuming here is this thread, the writer thread, has acquired this lock, currently, and so the reader thread, the first reader that is coming in, will not be able to proceed, so it will be sleeping here. Does that make sense? It will be sleeping here, but once, let's assume the writer is done, but once the writer is done, now it will wake up someone who's like waiting on this write lock. Let's assume this is the only reader currently that is waiting on this write lock. Now this reader wakes up, does a sem post on this particular semaphore called lock, just for this particular region of code, and then it just proceeds. So when it proceeds here, this will be the place where we would have our critical section basically. I mean, some person or like some person has actually acquired, some reader has actually acquired the read lock in this case, okay? But the important thing to note here is, if there are, like, when this reader is currently doing a read of that particular critical section of the, or the particular shared buffer, if there are like two more readers, this is reader 1, reader 2 and reader 3. If there are two more readers that have just come, what will happen to these two readers? The second reader will again acquire this particular lock, and immediately it will increase the number of readers to 2. Initially, the first reader was there, the value readers was just 1. Now the second reader makes it to 2, and this condition is not satisfied currently because this is not the first reader. This is like the second reader, and so we are not going to do a sem wait. Instead, we just assume that some reader who has started reading previously has acquired the write lock, and so now we can just go and start reading. So it does a sem post on the lock that we acquired at line 16 just for that particular piece of code. I mean, for lines, we just release this particular lock here, okay? We just release this particular lock, and immediately now the second reader has also entered the critical section, and it is also able to read the same data simultaneously with reader 1, and the same thing happens with reader 3. When reader 3 comes in, the whole purpose of having this particular semaphore lock, the use of the semaphore lock is just to guard the method acquire read lock, because two reader threads should not be acquiring the lock at the same time. That's the only reason why we are having that here. And so if only one thread, if the third reader comes in, again it increments this value by 3, checks that this is not equal to 1 because some threads are already there, and so immediately does not do a sem wait, immediately releases the lock that we got here and enters the critical section. And in this way, multiple readers can actually read from the shared buffer at the same time. Now let's assume if one of the readers is done. Let's assume if R1 is done. Okay, if R1 is done with its work, it's going to like release the read lock, and here again we are going to like protect this whole region of code of releasing the lock with the mutex called the semaphore called lock. Okay, just used as a mutex here. We just decrement this value by 1, decrement the readers count by 1, and check if this is the last reader. Okay, only the last reader. If we are the last reader, then this value is going to be 0. In that case, do release the write lock so that other writers who are interested in writing to the buffer can actually acquire the lock and then proceed. But if we are not the last reader in this case, when R1 just completed, R1 is not the last reader because in this scenario we still have R2 and R3, so it's not going to do a sem post on the write lock, but instead it's just going to release this particular lock and just proceed, but it just decremented the readers count by 1. Similarly, when R2 is done, this is going to decrease the readers count by 1, and finally when R3 is done, it is going to decrease this readers count to 0, and since the readers count is 0, this is the last reader that was actually using the read lock, and so now we do a sem post on the write lock, which basically means we are releasing the write lock, and so some other writer thread can actually now go and acquire the write lock. So the whole purpose of the reader-writer locks is to make sure if there is a single writer that is actually writing to the shared buffer, prevent all the other writers from writing and also prevent the readers from reading from the shared buffer. Okay, but if there is no writer currently, and if a thread starts reading the shared buffer, and if there are multiple other threads that are trying to read the shared buffer, allow those other threads that are just trying to read, but block the threads that are trying to write. So if there is like the reader just acquires the lock, and then immediately if there was a writer, that writer is going to wait till all the readers release the lock. Does this make sense? What is there any issue with this particular thing? This particular block? So the issue may be, okay, one of the issues is if the situation is like this, okay, if someone starts reading, like reader 1 starts reading, and immediately if writer 1 wants to write, okay, to the shared buffer, but there is another reader, reader 2, reader 3, then let's assume reader 1 is done now, okay. When reader 1 is done, immediately the writer 1 will not be able to acquire the lock because it has to still wait for these two readers to finish. It has to still wait for these two readers, R2 and R3, to finish. And let's assume after some time, if reader 2 is also done, then still we have to wait for reader 3 to finish. But before that, there may be some other reader that wants to read this particular thing, like R4 may start here. Okay? Some other reader may start here, and so this keeps on going, and only if both R3 and at this time, after this time, only if both R3 and R4 are done, and if there are no other readers, okay, before R3 and R4 are done reading, only then the writer W1 will be able to acquire the write lock. So basically, this particular reader-writer lock is not fair for writers. Okay? A writer can just starve continuously if there are like multiple readers that are coming in, and if it is doing a read. How can we prevent this? Based on some techniques that we saw previously.
Make a queue of readers and writers combined. So when you post, instead of immediately going to my reader, you might end up going to a writer.
Yeah, something like that. So very similar to the idea of ticket locks. We can just make sure that whenever someone comes, we can assign a particular ticket. We can use the idea of ticket locks along with this particular reader-writer locks to make sure that we can do something like queuing them up in the same queue, just to make sure that if there is a writer somewhere in the middle, we can make sure that the readers that have the lock previous to the writer should finish before we will allow the other readers to actually go and read the particular critical section. That is like one way that we can prevent this. Okay. Any questions on the reader-writer locks? Okay. When people like got interested in this field of concurrency, the person that we saw, Dijkstra, he actually posed a lot of interesting problems, which are like not practically relevant, but those were the problems that really are the classic problems in the field of concurrency. We are just going to look at one such problem called the dining philosopher's problem. So the problem that Dijkstra posed, this was like a class assignment, it seems, that he gave the students. I think at, he was from Europe, but I'm not sure. Like he also worked at University of Texas at Austin, so I'm not sure like where he gave this thing. But the idea is there are like 5 philosophers. Let's say P1, P2, P3, P4, and P5, and the things the philosophers each have a plate before them. and they have like 2 forks, okay? Like there are like 5 forks, F1, F2, F3, F4, and F5. There are forks like this, and all the philosophers, what they usually do is like they think for some time. They just keep thinking for some time, and when they feel hungry, they just like get the forks. They eat, and then they put back the forks. Okay? If this is if these are the sequence of steps that are going to do like continuously, okay, like you may assume like they do it in an infinite loop kind of. So the problem here is when this philosopher P1 wants to acquire like get 2 forks, then he can just take forks like the left fork and then the right fork, and then just start. If it is free, he can just pick up those 2 forks, start eating, okay, and then proceed. So we can just at the back of this reader-writer thing, we have described this problem. Okay. The basic setup for the problem is this: assume there are 5 philosophers sitting around a table. Between each pair of philosophers is a single fork, and thus 5 total. The philosophers each have times where they think and don't need any forks, and times where they eat. In order to eat, a philosopher needs 2 forks, both the one on their left and on their right. So you may think this is the sequence of steps that they are doing continuously, and you can also assume that we have like a semaphore here. Okay, you can consider these forks to be the semaphores. There are 5 forks. You can assume there are like 5 semaphore variables. Okay, and there are like functions like left and right, which just returns. Given the philosopher number, it returns the fork to the left of the philosopher, and given the philosopher number, it returns the fork to the right of the philosopher. And the mod is just to make sure that the 5th philosopher has the fork 1 to his right or something like that. Okay, and the task here is to see like how can we implement these 2 methods, like, or make this particular problem work. So the idea is the philosophers should be able to just do this continuously without any problems. Okay, so one scenario that we can think of here is just something like so all this line just means this, we are just calling a sem weight on the forks, the 5 forks, right? So for this particular philosopher, you can assume that the philosopher knows their numbers. So this philosopher is just trying to pick up his or her left fork. And similarly, once the philosopher gets that, philosopher may pick up the right fork. Okay, and you can assume we have the same ordering here, like sem post. So all we are trying to do here is like whenever a philosopher wants to pick up the forks, we are just having like an order between, like order in which they pick up the forks. First, each philosopher should pick up the left fork, and then they should pick up the right fork. And similarly, when they are placing the forks, they should just maintain the same order of placing the left fork first and then the right fork. So if this is the like algorithm that they are going to follow for picking up these forks, okay, do you see any problems here?
He gets the left.
Yeah. Yeah, it is possible that at a moment, like if everyone decides to pick the forks at the same time, everyone are going to like pick up the left fork, right? And the thing here is like no one is going to place the left fork back. Okay, they're just going to pick up the left fork and just they're going to wait until they can also get the right fork. So in that case, all the 5 philosophers have one fork and now no one can make progress. Again, a classic example for a deadlock. Okay? So how can we like avoid this? Can we modify the get forks in slightly in some way that we can we avoid this particular problem?
Could we put like a signal around to left and right? So the signal that one philosopher is picking up forks in general at that point in time? Or initial variable.
Okay, so you're saying like we can. So if you use a condition variable, you are saying like, okay, we are waiting, then if someone calls like wait on the condition variable, then are you thinking like, I'm not sure, like, can you explain?
Maybe the semaphore. Yeah.
Maybe just think about like, okay, one easy solution maybe, can we just have yeah, we have a solution. Yeah, definitely that can be one of the solutions. So just to think about this, okay, can we have like a lock around both these things? So in the sense, can we have something like a lock around these two things? Is that a solution? And if that is a solution, then is there any problem with that solution? I'm just saying if we have a lock, if a philosopher is trying to get, like, let's say the left fork, he has that particular global lock kind of. Okay, he gets the left fork, and then he gets the right fork, and then releases the global lock, right? But the problem in this situation is like when a particular philosopher is actually getting the forks, no, all other philosophers are basically blocked from getting their forks, even though their forks may not even be related to this particular philosopher. May not be besides this particular philosopher.
Can we, I think, like, put a lock around? I feel like what you need is a signal to tell them to let go of the left fork. They can't keep the right fork. So there's no reason for them to be holding the lock on the left fork.
Yeah, that's a very good thing. We will be looking at similar solutions. It's like if a particular philosopher acquires a left fork, and if there is a way that we can inform the philosopher, if you can't get the right fork, okay, just let go of the left fork, okay? If this was possible, yeah, then this is not a problem here, but assume that is not possible in this case, okay? So one easier thing that we can do here is, since there are 5 philosophers, you can just have something like just make one of the philosophers pick up the forks in a different order. So there are like 5 philosophers here, right? Just make P1 pick up the fork, the right fork first, and then the left fork, and all others P2 to P5, they pick up the forks in this order. Left fork first, and then the right fork. Just think about if this will work, okay? Let's just see this, okay? Let's assume P2 picks up this left fork. So P2 is having this, P3 is picking up the left fork, P4 is picking up the left fork, and P5, if P5 is picking up the left fork, okay? Then at the same time, P1 is trying to pick up the forks in the different order, in the sense like, yeah, so okay, at this time, okay, P1 has got the fork 2, P3 has got F3, P4 F4, and P5 F5. So the only person now who can make progress is, so let's assume P1, he will try to pick up the fork 5 first, right? The right fork first, but he will not be able to pick up, and so he is not going to pick up the fork 1, right? He's not going to pick up this fork because he is trying to pick up this fork which is already occupied, which is already taken up by philosopher 5, and so the only person who can make progress at this time is P2, right? Now P2 is able to pick up the right fork and then make progress, and then the assumptions are, okay, P2 picks up and then P2 just releases or keeps the 2 forks, and then P3 now will be able to make progress, and just this simple thing of making one philosopher pick up the forks in a different order just prevents deadlock in this case. All the philosophers can actually make progress. Any questions? How this works? Okay, if there are no more questions, then we'll just move to the last part of today's class. So we're just going to look at some bugs, common bugs that arise in concurrent code. Okay, the two major classifications are non-deadlock bugs and deadlock bugs. And this is classified into two types. Atomicity violation and order violation bugs, and we'll be like looking at deadlock bugs in much more detail, but let's just start with the non-deadlock bugs. So what do we mean by atomicity violation here is, assume there are two threads, and if thread 1 is trying to do something like and the non-deadlock bugs that we are seeing here, okay, in this particular case are actually from a research that was done by a professor called Shan Lu, and she was at UW-Madison, and she like took multiple real-world code bases like MySQL, Firefox, and stuff like that, and then she found out with her research group, she found out like the real bugs that are there, the concurrent bugs that are there in real world code bases. And this was like so frequently found, this type of bug. For example, I think this was in MySQL. So thread 1 is trying to do something like if thread.proc info, if that is like not null, then go and do some stuff, and let's assume we are also trying to use this thread.proc info in some way inside that particular if condition. And thread 2 does this particular thing. Thread.proc info, it just sets that thing to null, okay? And these things are usually, when we are looking at these things like next to each other, we can easily see that the problem is, okay, now thread 1 can check for that particular condition, and before it actually goes and finishes the lines of code inside the if condition, the thread 2 can actually execute, and thread 2 can easily make this proc info to null. And so at the time when thread 1 comes to this line, fputs and tries to use this thing, it is actually trying to dereference a null pointer, okay? This is definitely possible for us to easily see from here, okay? But the problem with real world code bases in this case is like these two things may be like at some irrelevant places, okay? The problem to figure this out is like here, the person who has coded this has just assumed that this whole thing is atomic, this whole if condition, or like checking the condition and printing some details about that particular proc info is atomic. But this assumption is not correct in this case, because some threads can do this particular line of code somewhere else, okay? And so just to avoid this, what can we do to avoid this, whatever we have learned till now? Exactly, we can just use some mutex logs just to make sure we can just add a log here and log here, and just make sure that it is atomic, in the sense the whole checking of the condition and using that particular structure is atomic. And similarly add the same log here, so that we can make sure that if some thread is already checked that particular condition to be not null, and if it is doing something inside that particular if condition, no other thread should be able to make that particular structure to become that particular variable to be null. Second problem, the order violation bugs. If there is a method called init, and if it is like thread 1 is executing that particular method, and if there is another thread T2, and if it is executing a method called main, what do you think is the problem with this particular code snippet that is shown here? There are two threads, T1 and T2. T1 is executing a method called init, and T2 is executing a method called main. So the problem here is, okay, this method main, this just assumes that this thread has already been initialized, okay? But there is possibility that T1 can run first, and then, T2 can run first and then T1. If T2 runs first, okay, then assuming mthread was initially null, then we are again calling, we are dereferencing a null pointer here, which clearly is a problem. So the problem again here is there was an assumption about the order in which these two methods run. So the person who just like coded this particular method assumed that, okay, I can directly use mthread because I assume that mthread is already initialized in the init method. But if these are run by different threads, then this need not be the case, because if these two threads were spawned at the same time, then thread 1 may have been created before thread 2, but thread 2 may just start executing before thread 1. Okay? In that case, we are going to again dereference a null pointer here, because mthread we haven't created or we haven't like initialized that variable called mthread. And how can we avoid this?
I have a question.
Yeah.
So are you saying something else ran mmain, the create thread from init did not run mmain?
Yeah.
It ran on its own?
Exactly. So the way that we can like solve this problem of ordering is just using some things like the condition variable. You can use condition variable with the state variable just to make sure that the thread 1 is run before thread 2. This is very similar to, you can assume this to be the main thread, okay, this part to be the main thread, and the init method to be the child thread that we created in our simple examples. In this case, we are just again enforcing ordering. If we can enforce ordering using condition variables, then these particular bugs may be prevented.
So is this the same kind of issue, like the missed wake up issue? Like would that be considered an order violation where a thread has a context switch before it can fully go to sleep, and then the next thread has to wake it up because it's not really asleep? It never wakes up. Everybody to sleep. Is that like the same type?
I'm not sure like which particular problem are you talking about, like producer consumer problem or
Any of the problems that involve going to sleep before, well, that involve the thread that sends a wake up signal, sending that signal before the other thread goes to sleep.
So if you remember, like we actually solved those problems using condition variables and state variables. And if you also use a state variable, then that particular scenario will not happen.
Is that an example of an order violation?
No, that is not even like a correct, if you think about that, that is not a correct way of using condition variables. If a thread goes to sleep and if there is no one else to wake it up, then it means like we haven't used condition variables in the proper way. So the way to use that is using condition variable. I don't think that is a problem that you're...
A bug, or if I write my code that way, that's a bug. Or are these just...
No, but here in these examples, it's more like the program is going to crash. In those examples, it's like they will be struck forever. I mean, they'll be just sleeping forever. Okay. So, you see this is in the book, okay? So in that particular research that Professor Shanlu did, these were the number of non-deadlock bugs that they found out, okay, in all these different applications. So MySQL, the database server was, they found out the bugs in MySQL, Apache, Mozilla, OpenOffice, and usually in these, the number of concurrency bugs, it's usually a lot. The non-deadlock bugs are usually more when compared to the number of deadlock bugs that they found out, okay. But I feel like the deadlock bugs are like more interesting. Let's just Okay, so deadlocks can happen like in situations like this. Let's assume if thread 1 is trying to acquire lock L1 and lock L2, and if at the same time if thread 2 is trying to acquire lock L2 first and then lock L1, then this is a case where deadlocks can occur. So there are two threads again, T1 and T2. There are like two locks that we have, L1 and L2. T1 has acquired L1 and T2 has acquired L2, and T1 is waiting for, let's just assume something like, if we have something like this, let's assume is waiting for, okay, this arrow just means is waiting for, T1 is waiting for L2, and at the same time T2 is waiting for L1, but L1 is with T1 and L2 is with T2. Okay. In this particular case, since there are two locks and L1 has acquired, so T1 has acquired L1, and if there is a context switch to thread 2, and if thread 2 acquires L2, at this time both will not be able to acquire the other locks that it needs, the other lock that it needs, because both have one lock each and they are waiting for the other lock to be released. There are four conditions, okay? There are four conditions that are actually necessary for a deadlock to happen. So the first condition is there should be mutual exclusion here. Second condition is hold and wait. Third condition is no preemption. The fourth condition is circular wait. And just to make sure, all these are essential conditions for a deadlock to happen. If we can prevent, or if we can just avoid one of these conditions from happening, then we can actually avoid a deadlock. In this case, if you think about it, now both these threads are trying to are trying to access some particular piece of code in an exclusive way. So they are actually acquiring locks, okay? So locks are involved. That's what this mutual exclusion just means, okay? They're trying to access some part of the code in an exclusive way. Hold and wait. Here, the problem, as you can just see here, thread 1 is holding the lock L1 and it is waiting for L2. Okay? And similar way, thread 2 is holding the lock L2 and is waiting for L1. Hold and wait is also a necessary condition here. Then the third condition is no preemption. So in this case, by no preemption, here we mean, even though thread 1 has acquired the lock L1 and it is not able to acquire the lock L2, there is no way for us to actually preempt. The thread 1 will not preempt the lock L1. It will not just release the lock L1 just because it is not able to acquire the lock L2. It will just hold on to it until until it can get the other lock. But there is no way that it can do so, and so no preemption is also a necessary condition for a deadlock to happen. And the last condition is whenever, like when something like this happens, like a circular wait, as you can see here, as a circular wait, like T1 is holding L1 and is waiting for L2. T1 is holding L1 and it's waiting for L2. And similarly, T2 is holding L2 and is waiting for L1. So there is a circular wait. And the solutions that we are going to see right now is like we are going to focus take one of these four necessary conditions, and we are going to see if we can attack one of these conditions, can we prevent deadlocks from happening, okay? And most of these solutions are used in like the code bases like Linux, we'll like talk about when we go to like particular solutions. Okay, so let's start with some easier solutions that we can attack. The first solution, all these things are prevention techniques for deadlocks. So the first thing is, can we prevent the circular wait from happening? How can we prevent the circular wait from happening? And you can again assume the same scenario, like there are two threads and they both of them need two locks. Okay, maybe even before we go to this thing, in like real world scenarios, like for example, if we are trying to, in Java, if you're doing something like adding two vectors, okay, like if you're saying like v1 dot add of v2, okay, this is happening, and if at the same time, if another thread is saying like v2 dot add of v1, so this is like a typical situation, because in this scenario, from the user's perspective, the implementation of the vector would be like hidden, right? Users would not really need to know about like how these vectors are really implemented. But if in Java, if these two statements are executed by two different threads, T1 and T2, then first this particular piece of code will try to acquire a lock on v1, and then it will try to acquire a lock on second vector. But if at the same time, if thread 2 is doing this particular piece of code, easily this particular thing can cause a deadlock. Okay? So the way we prevent, okay? So how can we prevent circular waits from happening? Any ideas? I think it's the other way around. So the problem that we just saw was very similar to that, in the sense thread 1 was acquiring L1 first and then L2, and thread 2 was acquiring L2 first and then L1.
Okay, so I guess require lock and not fashion.
It's more like if we can bring up an ordering of the locks, in the sense if you are going to acquire the locks, let's say L1, L2, L3 or something like that, just you should always, the thread should always acquire the locks only in this particular order. If this is enforced, okay, this particular ordering between the locks are enforced, and if the people who are using the code base are following this particular ordering whenever they are trying to acquire the locks, then this actually prevents deadlock from, because this easily avoids or prevents the condition of circular wait from happening, because in this case, see here, if this was the order that was enforced, then T1 can acquire the locks in this way, and there will not be any code. Okay, here it's not like people can't write code like this. If people write code like this, then it's going to cause a deadlock. But in a particular code base, if this is the way that we're trying to prevent deadlocks, then if this ordering is given, then we should not acquire L2 before L1. The two locks should always be acquired only in the order like L1 and L2, and this is called the total ordering of lock acquisition. And similarly, there is like a partial ordering too. Partial ordering of lock acquisition, which says something like, it just takes a set of locks, like let's say if you are acquiring these locks, then this is the order that you should acquire them in. Like, it need not be some total ordering, it can be some ordering, like let's say just L1, L2, L3. And if you are acquiring the locks L7, 8 and 10, L7, 8 and 9, then this should be the ordering. So it's like some partial ordering between a set of locks. So whenever you are acquiring locks, and usually it makes sense because people will not be acquiring locks like across these subsets that we have here. And so this is one particular technique that is used in the Linux kernel. You can just think about it as the ordering. We just order the locks in a particular way, and so if someone is trying to acquire locks in a different way, then those things would be like caught in the code review, and they will be like asked to change the particular ordering of the locks. But if people follow this particular total ordering or partial ordering, then we can prevent deadlock, because we will be attacking the condition of the circular weight. After that, circular weight cannot happen. The second condition that we are trying to attack here is hold and wait. Okay, let's just think about this, T1 and T2. Now these are like different solutions to solve the same problem. So in this, if someone is trying to employ this particular solution of attacking hold and wait, then in this particular case, locks can be acquired in different order. Let's assume lock L1 is acquired here, and then the lock L2 is acquired here, and this thread can acquire lock L2 as we did before, and lock L1. But here we are trying to attack the condition of hold and wait. So no thread. What does this condition mean is that we should not allow any thread to hold a particular lock and then wait for the other lock. So how can we do this? And assume there can be any number of locks in that particular code base, right?
Maybe like a taboo. Maybe that the first lock for a certain amount of time, so can't get trying to get that lock. Come back and say, "This is the lock." Can't handle it.
Yeah, so something like a timeout. How will we implement that in this case, in the sense? So here we are just trying to say, okay, if you are acquiring like lock L1, then you will not, for sure you should not be waiting for L2, right? So in this case, what we can just do is, one way to do this is just introduce a global lock. Whenever some lock acquisitions happen, okay, just lock the lock acquisitions with the global lock. So here what we can do is just this whole lock, this will be unlock of the global lock G. Similarly, here also we will be having a global lock, and then we will unlock the global lock. So now this makes sure that whenever a thread is trying to acquire the locks, it can acquire like locks in any order, but before acquiring the locks, it should have this global lock. Okay, only then it will be able to acquire the locks. If we do this, then we again attack the condition of hold and wait. Hereafter, no threads can actually hold a particular lock and wait for another lock, because now it has like exclusive access to almost all the locks that are there. Okay. What is the problem with this particular solution?
Having two locks.
So one thing is like this reduces like concurrency. If you think about it, whenever someone is trying to acquire certain locks, that particular thread holds the lock. But if some other thread is trying to acquire totally different set of locks, even then it's going to acquire the global lock, but it will not be allowed to acquire the lock until the first thread finishes. Okay. So concurrency is going to decrease in this particular case. We have like two more solutions to attack the other two things, which is no preemption and mutual exclusion. I think we can take a break right now, and after the break we can just like finish that off, and then the third prevention technique is to attack a condition called no preemption. So this problem was no preemption problem is a thread acquires a lock L1, and if it is not able to acquire the lock L2, it will not release the lock L1. So can we do something to actually prevent this particular thing from happening? So it's more like, let's assume there are two threads, okay, T1 and T2. Thread 1 is trying to acquire the log L1, okay. There is a primitive, even in pthread library we have this primitive called try log, okay. There is something called try log. So it says like, before acquiring the second log, just directly don't go and acquire the second log using a log of L2, but instead just do something like a try log. Try acquiring this log L2 if you are able to, okay. So if you acquire L2, then it's going to return, try log is going to return 0, which means like we were successful in acquiring the log L2. But if not, okay, if it is not, if the return value for try log is not 0, then what you're just going to do is you're just going to go and release, unlock the log that you had previously, which is L1, okay. Just go and release the log L1, and you're just basically, you should start trying to acquire the log L1 all over again. Does it make sense? When you're not doing this, just so have like a label like top or something here. Just going to say go to top. And similarly in thread 2, this is going to be like, you can think of this like it's trying to acquire the log L2, and then it will be doing a try log for L1. If it is not 0, then it will just unlock L2, and then it will again go and retry all over again. So this is how using primitives, like using these primitives like try log, which is available in pthread library, we can actually prevent the necessary condition called no preemption. But there is like one problem that can happen here. Can you think of this? Again, try explaining this one more time. So here, thread 1 is trying to acquire the log L1, and then it is doing a try log on the second log L2. So if it is not able to acquire L2, it just releases L1 and then tries acquiring L1 all over again. Similarly, thread 2 does the same thing in the reverse direction. It acquires L2, and then if it is not, if it does a try log on L1, and if it is not available, then it releases L2 and just tries this all over again. But one problem that can occur here is, let's just name these like, let's just name these lines as A1, A2, A3 and A4, okay, and similarly B1, B2, B3 and B4. If the sequence of code execution is like A1 is acquired, say A1 is executed, so thread 1 has the log 1, then if B1 is executed, then thread 2 has log 2, then if A2 is executed, so now A2 will fail, okay, try log is going to fail in this case. So again, at the same time, if B2 is executed, these are the sequence of operations that are executed, then we are going to like release this log A3. Similarly, thread 2 is also going to release the log at B3. Then both are going to execute A4 and this is going to execute B4, and then the same pattern may continue. If the same pattern continues multiple times, okay, there is a possibility that both these things are just doing the same thing all over again. So again, this will go and acquire log L1, at the same time this will acquire L2. If this sequence of events can happen, then it is not really a deadlock, because both the threads are not actually locked completely, in the sense without making any progress. They are trying to make progress, but no real progress is actually made. And so this particular situation, where both the threads are just trying to acquire the logs continuously, is called live lock. Yes, the live lock is a problem that can happen in this particular case. The two threads are not deadlocked, but they are actually live locked, because like because it is possible that this sequence of events can just happen continuously. And the way that we can prevent this is, any ideas how can we prevent this?
Yield before going to top.
yeah, something like yield before going to top, or like just introducing some random delay in between the time that we are actually doing the lock and the try lock. If we can introduce some random delay between the time that we're doing the lock and the try lock, then we can actually avoid this particular live lock problem. Okay, the last thing is actually the most difficult thing to prevent. So now here we are trying to attack the condition called mutual exclusion. So can we attack mutual exclusion? Mutual exclusion is like whenever you acquire a lock, we are actually having mutual exclusion. So the idea here is like, can we not even use locks, okay? So people actually came up with a solution called lock-free data structures. Or you can also weight-free data structures, where the idea is, if you remember, we're going to like look at the primitive like compare and swap, okay? So this is going to be useful in implementing these. Remember the hardware primitive that we saw previously called compare and swap, where we have like an address passed in, we pass in some expected value, and then we pass in some new value that we want to update in that particular location. So in this primitive, what was happening is, if the value in that particular address, if it is equal to the expected value that we just passed in, then we update that particular value inside that address to the new value, and then we return 1, which means success. Okay, if that is not the value that is found in the particular address, just return 0. Okay, this was what we saw with compare and swap. Now the idea here is like, can we use a primitive like compare and swap, okay, which is some powerful hardware instructions that the hardware provides. Can we use these instructions to actually write lock-free data structures? So one simplest example is called atomic, like an increment. We can have something like an atomic increment. Here this method is going to increment the value at this particular location by amount times, okay? It's going to increment the value at this location by amount times, and we want to do this atomically. And one way to do this is using this compare and swap. You can do something like, okay, you can get the old value at that particular location. Okay, you can get the old value at that particular location, and then just write in a do while loop. Okay, so I'm just writing compare and swap here. Okay, you see I'm going to use compare and swap, and this is the whole thing. This is the important thing here. How are we going to use this compare and swap? We are saying this is the value that we are trying to update. We are passing in the old value here. The old value is nothing but the value that we just got from that memory location called old, and the new value that we are trying to update this particular memory location is with the value old plus amount. And we are going to check this particular thing if it is equal to 0. Okay, if it is equal, if this whole condition, if it is equal to 0, then do this do while loop again. But if it succeeds, then just like exit. This is like very interesting. So if you think about this, okay, so let's assume this is the location that you're trying to update. This is the memory location that you're trying to update, and initially let's assume the value is 0. Okay, when we use this atomic increment to increment this value by, let's say, 1, in that case amount is going to be 1. We will be getting this old value, okay? We will be getting this old value inside the variable called old, and once we get this old value inside this variable called old, here in this compare and swap, we are saying this is the expected value that we are expecting at that particular location. So we already took that value of 0 and have it in old. We're saying like in this particular memory location, I am expecting the value to be 0, and if so, okay, if that value is 0, update that value with a new value called old plus amount. Okay, so when we are doing this, since it is atomic instruction, we are going to see this. Yes, it is 0. So I'm going to update it with the value of 1, assuming amount is 1. Then the compare and swap is going to return 1, which means success, right? So then this is going to be done, and we are done with atomic increment. But just in case, let's assume after we took the value of 0 inside this variable called old, if some other thread comes here, okay, if some other thread intervenes in the middle, and if it has updated this value to some other value, let's say 2 or something like this, now when we do a compare and swap on this particular thing, we are going to check, okay, I have took this value and I'm just going to check if the value that is inside this memory location, if it is still 0, in this case it is not, because some other thread has already updated that value to be 2, and so what will happen is this compare and swap will not update that particular value because the expected is not equal to the current value in that particular address. In turn, it will just return 0. So once it returns 0, we will go back to the do while loop, and now we will get the current value again. Whatever value we have there in that memory location currently, we will get that as the old value and try to atomically increment that. Does that make sense? This is like a scenario like where we can use something. This particular thing is, we don't really use locks here, but we just use some powerful hardware instructions that the hardware provides to do an increment in an atomic way. We can also use this to, let's say, insert an element in a linked list without actually using locks. So let's just see how we can do that. Okay. So let's assume we have this particular method for inserting at the beginning of a linked list. It just takes some value. Create a node. We do an assert just to make sure that malloc succeeded. Then we just fill that node's value with the new value that we got here. And now usually this is going to be like n dot next will be whatever is pointed to by the head currently, and then you'll go and just update the head to be this particular node. And let's assume this is the normal insert at the beginning code that we have for a linked list. Okay, now the task is, this is just next. Okay, it's next. Now the task is, we know like these two lines are critical section here. And as we already saw, we can do this atomically using locks by using mutex locks around these two lines. Okay, assuming malloc is thread safe. Assuming malloc is thread safe, we can just protect these two lines of code with locks. But now the task is, can we use compare and swap, okay, to actually do this in an atomic way, do these two lines of code in an atomic way, okay, as we saw in atomic counter. So just the high level idea is just going to be, again, I can just write down something like a do. Okay, you are just going to think about what should be the statement or the statements here inside the do, and what is going to be the condition that you are going to give to compare and swap. What should be this? What should be the second argument? What should be the third argument? Still you are going to check if it fails. You are just going to do the do while again. So just think about, and here we are only focused on these two lines of code. Okay, what should be the line of code that should come here if you want to use compare and swap and avoid mutual exclusion or avoid using locks in this case, but still the insert should be done in an atomic way. Definitely this line of code, okay, this is going to be here because we will think about the diagrammatically in a few seconds. Just going to have something like n dot do this, update the next variable in our current new node that we have to point to the head, okay. But before you try to update the head, we are going to use the compare and swap. So it's more like pass the address of the head here. Okay, this is the variable or this is the location that we are going to update, and the value that we are expecting there is nothing but wherever value inside head is the head that this node is currently pointing to. So this node is just currently pointing to the head. So that we are assuming maybe that is the value that should be there. Okay, the expected value. If it is there, just update the head with the value of the new node n. Else, just go and do this all over again. The diagram may help here. So let's assume this is the head. Okay, and assume there is just a single node in the linked list currently with the value of 1. When we are doing this insert, we create a new node n. So here this is the pointer to a node n. Let's assume we have a value of 2 now. Okay. And when we come here, we are just saying n dot next equals head. So whatever head is currently pointing to, okay, just make this point to the same thing. But before updating the head, we are using compare and swap. We are saying compare and swap. Just go and check if the head that we are trying to update still points to the first node in the linked list. Okay, if it still points to the first node in the linked list, this is nothing but the expected value. So which is nothing but n dot next is this first node. So if it is still pointing to the same node, then go ahead and update the head with the value of the address n that this n is pointing to. Then make this the new head. Okay, so now this will be gone. So now this thing, this insert at the beginning just happened successfully. But the other scenario is the same way. If there is this head, and if we have like this node 1, okay, assume when this we updated the next pointer of this to point to this thing, but before we updated the head, okay, but before we updated the head, there is a possibility that some other node actually inserted a new element in this place. At that time, the head would have changed its value. The head may be pointing to now. Let's assume there is a node with value 3. Now this is the new head. Okay, so now when we do compare and swap, we are going to compare this address, okay, address of node 1 with the address that is in the head currently, which is some other node. So using this, now we can know that the head has actually changed. Okay, the head was changed in between. Before we took the value and assigned it as this node's next node, and between the time we updated the head. And so now what we can do is just go and do this whole thing again. So now this just failed, so we can just do this whole thing again. So when you're doing this whole thing again, we're just going to now say n dot next is equal to the new head, or whatever head is there currently. So now n dot next is going to not point here, but instead it's just going to point to the node 3. And at this time, assuming no other node came in the middle and inserted a new element, we can be sure that, okay, now we just changed the next pointer to our node the second time, pointing to the current head. And at this time, when we are trying to update the head, again we are going to check, is this address equal to the address? Is the next node that we have here, is it the same as the node that the head says it's pointing to? If it is the same, just update the head. Just update the head to point to our node. That's all that's happening. And in this way, we can actually implement this. But again, as you can see, just with a simple insert like this, it wasn't like really easy to come up with whatever we have here. And so even though these are possible, you can think about what happens if you're going to like use hash tables and stuff like that. And these things may not be like really, these lock-free data structures, although they are there, they are not like used so often as locks. Okay, but this is possible, and in this way we can attack the fourth condition called mutual exclusion, and then this can be done. Okay, and we can avoid deadlocks. So one other way for avoiding deadlocks is like it's called the ostrich algorithm. Okay, where it's more like the ostrich. Whenever it predicts some bad thing is going to happen, it just like inserts head inside the sand, and then it assumes that okay, I can't see anything, and so nothing bad is going to happen, or I'm safe, or something like that. And not joking, like this was the solution. Like previous versions of Windows and some of the operating systems were actually using for deadlocks for personal computers in a way like if deadlocks are going to happen in the code base like just maybe once in a year, it's not really worth to spend engineering resources to actually try to see how are we going to like avoid deadlocks. If it just happens like once in a year, it should be just fine. You can just press the restart button and the operating system will just restart. But again, if we are thinking about writing code for some space shuttle or an airplane or something like that, again, we should not be definitely using an algorithm like the ostrich algorithm, where we just think like we don't worry about deadlocks and so deadlocks will not happen or something like that. We should be really careful in whatever we are going to do. So with this, we have basically completed the part on concurrency, and from the next lecture we will be going into file systems. Any questions about deadlocks, about these lock-free data structures, or anything that we just saw? Okay. I think I'll just hand over the